Hello everyone, I'm Chenle from Barcelona Supercomputing Center. Today I'm going to present the Taskgraph framework developed at BSc that aims to reduce the OpenMP tasking model's overhead. And this framework is introduced in OpenMP 6.0. So the syntax of it is going to be released along with the 6.0 specification. First, let's look at what motivated our work. Here I'm showing a CPS, Cyber Physical System application called Adaptive Optics. So what it does is it will capture images from a star, and the captured image is distorted because of the atmosphere. This distorted image will be sent then to the wavefront camera represented in the diagram, and this image will then be compared to the expected image to compute a set of errors, and these errors they will be sent to the control system, where based on the errors a set of control command will be computed as a vector. So eventually this vector of commands will be sent to the defaultable mirror, and the mirror itself will adapt its shape in order to correct the image, the upcoming image, so that the correct image will then be sent to the science camera. And on the right hand side of the slide we see how this application can be parallelized or pipelined using OpenMP. Another example is iterative applications. So I'm showing here an animation of an body simulation taken from Wikipedia. And the idea is the same as the adaptive optics. That is, these kind of simulations, they have high performance requirement because they need to be computed hundreds, even thousands of times every second. And also, they are repeatedly executed. So, say we have the OpenMP application as shown on the right-hand side, and the overhead of tasking model is high. Then we need to pay this overhead every single iteration. But I think we can do better. This is what we want to achieve with the Taskgraph framework, to reduce the overhead of OpenMP tasking model, to lower as well the contention on shared resources. And once the graph is built, we believe there is a way to map these graphs to other programming models such as CUDA or HIP for NVIDIA and AMD GPUs respectively. So how the Taskgraph framework is working? It's declared inside of a parallel single region where only one thread will start to record the graph. And once the graph is recorded, at the second time when the Taskgraph directive is encountered, there is no need to create task instances and solve the dependencies anymore, because we have the graph already in the memory. And we can also map these graphs very easily to, for example, CUDA graph, because we know the dependencies among the tasks already as well. I will show in detail how this framework is implemented. But before, I want to give an outline of this talk. And we will continue with a syntax review of the Taskgraph directive that is going to be introduced along with the OpenMP 6.0 specification. And I will explain as well how the graph are generated in the compiler in the runtime, more specifically at runtime. Also, I will give the performance numbers of these graphs with the host tasks first, and we will see how we implement the map of host graph to device graph using LLVM compiler, and then a set of evaluations of the device graph with the GPUs before we conclude in the end. Let's look at the syntax of the directive. The complete syntax is already in the technical report, which is on the OpenMP website. Here I'm going to explain two important clauses of the directive. So the first one is the graph ID, which takes an integer as the argument. And what it does is it acts like an identifier of a graph. So let's look at the example on the left-hand side. If operation loop is called multiple times with different num, then since we are using the num as the argument for graph ID, so we will create also multiple graphs based on the single Taskgraph directive. And what if we want to, for example, erase a previously recorded graph ID with the ID 1, for example, then we can use the graph reset, which takes a boolean as the argument. So what it does is if the boolean condition is true, then instead it will erase a previously recorded graph with the graph ID specified, and the new graph that is going to be recorded will be stored for that specific ID. Now let's talk about the graph generation in the compiler. So how it works? Well, it depends on which information is available at compile time. So let's look at the optimal case, the output C in the diagram, where we have the tasks, the task dependencies, as well as the task data. Everything is basically known at compile time. Then in this case, we can generate a complete task graph. So at the runtime, when we encounter the Taskgraph directive, we can right away start to replay the statically generated Taskgraph instead of recording it. So if we only have the tasks and the task dependencies at compile time, but not the task data, the output B, then we will create partially the graph, so the edges among the tasks can be created at compile time, but not the task along with the data. Then in this case, at a runtime, we will record the tasks with their data, and this task graph will then be ready to be replayed if we encounter for the second time. Similarly, for the output A, where we don't have any information available at the compile time, then we will need to record everything, the task, along with the dependencies and data, to form eventually a graph ready to be replayed from the second iteration. And then again, the detail of this implementation can be found in the previously recorded published paper. The DOI is given here. So next, let's look at the evaluation numbers from the Taskgraph framework. But before that, I would quickly give the setup we used to get the numbers. So all the experiments were carried out on a node of my Nostrum 4 supercomputer. I used a set of different applications. They can all be accessed in my personal GitHub. The address is also given as well. And on the right hand side, I'm showing some environment variables to configure the execution as well as the optimization flag, all three used to compile everything, well, all the applications. Let's look at the overhead reduction first. So here I'm showing the numbers from both compilers, the LLVM compiler, but also the GCC compiler, because we have a preliminary implementation of that Taskgraph framework in this compiler as well. And the code is also given, and it generates a graph represented as a diagram on the right. So in this case, we are fixing the problem size and we vary the number of tasks. So we see that for 100,000 tasks, GCC spends about 3.5 millisecond to execute the whole application, whereas if we include the Taskgraph framework into it, it spends only 345 milliseconds to execute. So we see a 1 order of magnitude speed up gain here. But for the LLVM compiler, we managed to reduce the execution time from 460 milliseconds to 130 milliseconds. Still, the performance gain is large, but not as good as for the GCC compiler. This is because in the GCC compiler, all the tasks, they are scheduled in the centralized queue, which causes a large overhead on the contention to access to this queue. The detail is not given here, but I think it's fairly simple to find more about this in the literature. Now let's look at the normalized speedup of the Taskgraph framework against the vanilla tasking model. In the heat maps shown here, the y-axis corresponds to the number of tasks and the x-axis is the number of threads. And the numbers, they correspond to our expectations, because we have seen that the Taskgraph framework, it manages to reduce the thread contention. That means for a high number of threads, the performance gain is going to be larger. So we see that for 32 and 48 threads, we see a better speed up for Taskgraph than the vanilla tasks. And this is also the same for the number of tasks. So the more tasks we have, the more overhead we are going to pay, because we need to create these tasks and also solve the dependency relationships among these tasks. So this is why as well we have higher normalized speed up on top of these heat maps. So the same trend can be seen for the comparison against the vanilla task loop construct. Again, here in these heat maps, we have the y-axis representing the task number or the task granularity, and the x-axis representing the number of threads. So these numbers, they are similar to what we have seen previously, because we see a higher normalized speed up on the top and on the right of the chart, meaning that the Taskgraph framework, it provides a better speed up when there are many threads and when the task number is large or the task granularity is very small. There is one comment that I need to precise is for these numbers, I gathered them with the NPB, so the NASA parallel benchmark, but not all the applications inside this benchmark suite are reported, because some of them, they are not suitable for the Taskgraph construct. And again, more details can be found in the paper that I have shown previously. Now that we have seen that with the Taskgraph framework, we managed to gain performance, at least for host tasks. What about for device tasks? So first, a very quick motivation for this work, because nowadays, more and more supercomputers, they are integrating GPUs as a alternative computing resources. So 9 out of 10 of the top 10 supercomputers in the world right now are using GPUs. And for this for this GPU computing, there is a new execution model introduced, which is called the GPU graph. So first introduced by CUDA, named CUDA graph, and then AMD adopt this concept and create the heap graph, so their own version of GPU graph. So the reason why they have both introduced this execution model is because each submission of a GPU kernel from the CPU, it costs a synchronization overhead, as we can see in the chart in the middle. Instead, if we can wrap all these kernels together with the data needed for these computations, and only we submit all the kernels once, then we are paying this synchronization between the CPU and GPU only once instead of many times. And this execution model is particularly interesting in the examples that I have shown at the beginning, where we need to repeatedly launch the kernels. And on the bottom, I just gave a set of functions that are needed to create such GPU graphs. So I'm going to present very quickly the implementation of how we map the host task graph to the device graph in LLVM. So let's look at first at the code I'm showing. So again, it's similar to what we have seen previously. We have a task graph region in which we defined our own tasks with their dependency relationships. So first, we will create a proper task graph with the dependencies among the tasks, and then we will create a virtual graph on the offloading runtime inside the LLVM compiler. So why this graph is virtual? Because this allows us to adapt this framework with the future GPUs or accelerators, because if we want to extend the implementation, then we just have to implement the virtual functions of this graph, and eventually they will be ready to go. So before showing the numbers of the device graph experiments, I will give a very quick setup description of these experiments. So this time I have carried out the experiments on 3 different platforms. The first one is the most powerful one, is a node from the Nostrum 5 supercomputer, so 1 generation newer than the Nostrum 4. And it has 2 powerful CPU, resulting in total 80 CPU cores, and as NVIDIA H100 as GPU. The second one is it has a customer level GPU, NVIDIA RTX 4080, and the third one is the least powerful GPU, which is embedded into the ARM CPU architecture as a system on chip. And the applications, again, they can be found in my personal GitHub, but also I have produced a tarball that is makes easier to reproduce these experiments, again with a set of environment variables that I used throughout the experiments. So first, let's look at the mean execution time the task graph managed to reduce on the GPUs. So here I have gathered the numbers from a NVIDIA GPU for, on the left hand side, the customer level GPU 4080, and on the right hand side, some numbers from the data center node. So what we are seeing here is the normalized speed up again on the y-axis, and on the x-axis they represent different algorithms applications. So generally we show that our bar, so the device graph, they have a better normalized speedup than the teams distribute, which is like the for construct on the device. And the baseline here, so the blue horizontal line corresponds to the vanilla tasking model on the device. So basically the idea is with the task graph framework, we not only outperform the vanilla tasking model on the device, but also most of the cases we outperform the four offloading mechanism on the devices, the SPMD model. Then let's look at the scalability test result from the task graph on the GPUs. So I show here the heat propagation on the left side on the data center node, and the n-body simulation on the right hand side of the slide, again on the data center node. So we are varying here the number of tasks or the number of nodes in the graph. And again, for these charts, the y-axis, they represent the normalized speedup, and on the x-axis, they represent the number of nodes in these graphs. So we see that the speedup gain is more important when we increase the number of nodes. That's because the vanilla tasking model, it will incur even more overhead with more number of tasks, and this is not the case for our task graph framework. So to end with the comparison, we are here now comparing with the vanilla CUDA because we spent some time to implement the benchmarks with the pure CUDA, so we don't have any overhead related to OpenMP. So of course, if we do this effort, then the CUDA has to outperform the OpenMP version, even enhanced by the Taskgraph framework. But if we focus on the numbers gathered from the Mare Nostrum 5 supercomputing center, we see that with the device graph, we do not need to write any single line of CUDA, but still we are able to provide a final speedup of 2.2x compared to the original tasking offloading model, whereas the CUDA is faster. It provides 2.7x of normalized speedup, but it requires much more effort to implement. So to conclude, the task graph directive syntax is now in the OpenMP 6.0 specification, And with our result, we are able to demonstrate that with the framework, we can enhance the speed up for host tasks, but also for OpenMP offloading model. And it enhances then the performance of OpenMP, but also the interoperability of it, because we can map such graphs to GPU graphs. And I have to say that for now, we have the implementation mainly internal to BSC, but we look forward to upstream to provide this implementation to the upstream LLVM implementation. This is a ongoing work. We have started already with the host part of it. And also we look forward to tackle the restrictions of the implementation, because for now we have only implemented the GPU part for CUDA GPUs, but not for AMD GPUs, and we look forward to complete this implementation. So with this, I thank you very much, and if you have any questions, please do not hesitate to write to us. Thank you.